Okay, hi everyone. So we are now on the second part, which is the second law of thermodynamics. So remember, we discussed the laws of thermodynamics by looking at how we can destroy heat inside the house during a hot summer day. Now let's take a look at the third one. We have here, can we convert some of your home's thermal energy into electrical energy? So what do you think? Now you can see here, you can easily convert ordered energy into thermal energy, but the reverse is much harder. So we are going to look into the details of this as we discuss more about the second law of thermodynamics. And also, systems that begin with some order or some amount of order gradually become more and more disordered. And disorder of an isolated system also never decreases. Those are the concepts of second law of thermodynamics. But let's take a look at these examples. Now the think about the mechanical energy transformation if you have a ball and then you try to drop the ball. We have here the potential energy can easily be converted to kinetic energy, and that can also be easily converted to thermal energy. But the reverse would be very difficult or would be impossible. Let's say you have the ball and then the kinetic energy or the thermal energy will be converted to kinetic energy, and then the kinetic energy will be converted to potential energy without lifting the ball. So same thing with this. If for example you have a cup and then you drop the cup and then it's broken, so it would be very difficult to have the cup na it would be very difficult to reverse the process of forming the cup again without those marks. Okay? So if we are going to look at, let's go back on this one. If we are going to look at this based on the laws of thermodynamics, if it is possible that the kinetic energy, the thermal energy, can be converted to potential energy, it will not be contradicting to the first law of thermodynamics because energy can still be conserved. But if we are going to think about it, this doesn't happen in nature. Same thing with this. And then looking at this. If you have, for example, ground pepper in a different layer, and then you have another layer of salt. So we have first layer of ground pepper and then second layer of salt. Then you mix them all together. You will observe this second illustration. And it would be very difficult and it is almost impossible or it's impossible to separate them again into different layers or into two layers. Okay? So that is about the second law of thermodynamics. Another one. Sinipag ka. Nag-aral ka, but sinipag ka ayusin yung table mo. So it's very organized. But you expect or you would expect that after maybe finishing this module, your table or after solving physics problems, your table will be disorganized. But you have to exert extra effort so that your table will be organized again. Okay? So I hope you are now following the concept of second law of thermodynamics. Okay, another example is this. If for example, nag-away kayo, nagkaroon ng lamat ang inyong love life. So you have to exert extra effort so that it will be that you can mend it. But meron na ring lamat. Okay? So that would be very difficult also. Mabahirap daw ibalik yung tiwala. So those are all related with the laws of thermodynamics. They have thought of, yung first law is concerned about conservation of energy. But they are thinking of those processes in nature which are not reversible. Tells us, the second law of thermodynamics tells us that the entropy of a thermally isolated system of object never decreases. So it's always increasing. And entropy is related with disorder. Heat will never itself flow from a cold object to a hot object. Now, it's very easy for an object to transfer energy from a higher temperature object to a lower temperature. But the flow from the cold object to the hot object will be impossible. It is impossible, or heat will never itself flow from cold object to a hot object. It is impossible for any system to undergo a process in which it absorbs heat from the reservoir at a single temperature and then completely convert that heat into mechanical work, with the system ending in the same state in which it began. So, mahirap na siya ibalik. Like, as I have mentioned, an object being dropped, it could be easily converted to thermal energy, but that thermal energy being converted to potential energy is irreversible. Okay. The second law is also related with how heat engines work. So we have here a heat engine. It is any device that transforms heat partly, take note, it can only transform heat partly into work or mechanical energy, but not transforming all the thermal energy completely to mechanical energy. All heat engines absorb heat from a source at a relatively high temperature. So take a look at that. There should be a hot reservoir and then perform some mechanical work, which you can see here, and then reject some heat at a lower temperature, which is the cold reservoir. So let's describe it by using an equation. Okay, we have in the illustration an energy input at QH, or at a higher temperature. Partly, that energy can be converted to work, but some energy will just be dissipated at the cold reservoir. So this equation can describe our heat engine. Now let's take a look at the processes for a gasoline engine. Okay, let's take a look at the processes for the gasoline engine. We have here the intake stroke, the compression stroke, then the power stroke, and then the exhaust stroke. Now, if the piston will move down, so the piston moves down, that will be the intake stroke. So the gas enters the system, the gas and air enters, and then you have here, as this one moves, it will be compressed. The gas inside will be compressed. So upon compressing it, the pressure increases. The volume decreased because of compression, then the pressure increases, the temperature also inside increases. So that there will be an combustion of the gas. So that one we call this a power stroke. Okay, now we have here the exhaust stroke wherein the burned gas will move to the exhaust of the system. Okay, so this is how the gasoline engine works. We have the intake stroke wherein the piston moves down so that the gasoline air mixture flows through an open intake valve. So it enters the system. And then you have here the compression stroke. Intake valve closes and the mixture is compressed adiabatically. So when we say adiabatically, Q is equal to 0. No heat is added on the system or released by the system, but because of the compression at this point, A to B, since you have seen here, there's a initial volume to volume 2, so it is compressed. So what happens here is that the pressure increased. So that is the compression stroke A to B, and then from B to C, we now have here the higher temperature. So what happens here? The volume is the same, but the pressure has increased. Okay, now looking at B to C, we have here QH is added to the system. When the spark plug ignites the mixture, so the heat is added to the system. Okay, so looking at point B to C, we have here an increase in pressure. And also we have the heat added to the system. So that is the ignition or the combustion. Then after that, we now have from C to D, because of that pressure inside, so that gas can do work on the system. So again, you can see the volume has increased from point C to D. If the volume has increased from point C to D, that means that work is done by the gas on the system. And then here, you can see now here, the exhaust. Same volume, there's no change in volume, but there will be lower pressure now, or the pressure has decreased, and then the burned gas will now be exhausted, or will exit the system, and then the cycle begins. So that's how the gasoline engine works. Now let's take a look at the efficiency of the heat engine. Okay, again, recall that we have, for the heat engine, is described as Q, or QH, is equal to the work done by the gas, and then you have here plus QC. So when we say efficiency, it tells us about the output and the input. So that's the ratio of the output to the input. So we have here work is the output, and then the input will be QH. Now let's derive further. We now have, based on this one, we have here, let's try to express them using QH and QC. So let's derive an equation for work based on this. We have work is equal to QH minus QC. So let's substitute that to this. We now have another equation for the efficiency, E, QH minus QC over QH. So based on that, another derivation would be, we can just express this QH divided by QH as 1 minus QC over QH. So that will be the efficiency of our heat engine. Okay, so that will be our equation. Okay, next, we will also try to solve problems on this one. Okay, next is that let's talk about the diesel engine and how it's different from the gasoline engine. Okay, for the diesel engine, it operates same as the gasoline engine. However, there are no more spark plugs involved. Fuel is directly injected in the cylinder just fast enough to keep the pressure approximately constant during the power stroke. Because of the high temperature developed during the adiabatic compression, the fuel ignites spontaneously as it is injected. Unlike in the gasoline engine that you have to have the spark plug to initiate the ignition. So that is the major difference between the gasoline engine and the gas engine. Okay, now let's talk about the Carnot engine. Now, a French scientist, Sadi Carnot, has thought of how can we increase the efficiency of the engine. So he came up with this ideal heat engine, which is the Carnot engine. Now let me explain the different processes involved in the Carnot engine, or the different thermodynamic processes. So you have here isothermal expansion. So when we say isothermal again, there's a constant temperature, and its expansion, therefore it means that the volume will increase. So that is from point A to B. So you can see here from point A to B, it's at a higher temperature. There's a constant temperature since from the term isothermal. And then at this point, the system absorbs the heat, QH. Okay, during the expansion. Yes. Next is an adiabatic expansion. From the term adiabatic, so there's no heat transferred to the system or into or out of the system, but it will drop. It drops from TH or higher temperature to lower temperature TC. And the next would be from C to D. So you're looking at this point from C to D. So you can see here that the volume has decreased. So that is an isothermal compression at a constant temperature Tc. And then the last one would be the adiabatic compression. But for the isothermal compression, we have now here it will during the isothermal compression, we now have here it rejects heat at a colder temperature Qc. So that would be the exhaust. And then from B to A, there's an adiabatic compression. Again, no heat is added or flowing out of the system, but it will move or it will be back to its initial state at a higher temperature TH. So that's the Carnot engine. But that one is an ideal engine. So let's take a look at the efficiency of the Carnot engine. So Carnot engine is considered to be an idealized reversible engine, wherein the heat QH and QL are directly proportional to TH and TL. So recall that we have an efficiency before. Okay, we have QH is equal to work. Then we have plus QC. And then we had an efficiency wherein work QH minus QC is equivalent to QH. So that one, again, QH is proportional to the temperature, higher temperature. Then QC proportional to the temperature, lower temperature. And then you have here TH. So the efficiency for this would be equal to 1 minus TC over TH. So that's for the Carnot engine, or which has an ideal efficiency. Or you can see here that we can only attain an efficiency equivalent to 100% if you have here TC or colder temperature at an absolute zero temperature, which is 0 Kelvin. But reaching 0 Kelvin is impossible. So that means that it's also very impossible to have a heat engine which is 100% efficient. So we can consider the Carnot engine as an idealized model or as an ideal heat engine. So we can also state that no device is possible whose sole effect is to transform a given amount of heat completely to work. So as I have mentioned, it would be impossible to convert all heat or all thermal energy to work or mechanical energy. Okay, now let's take a look at the refrigerator. A refrigerator takes heat from a cold place and give it off to a warmer place. Now that requires input of mechanical work to take heat from a cold place. So that means it has to consume electrical energy. Okay, so you can see here that the work is added on the system so that you can transfer from a lower temperature body to a higher temperature body. A work is added, and that is the role of electricity. So you have here the efficiency for the refrigerator. We have QC over the work, or equivalent to QC over QH minus QC. Okay, so now let's talk about entropy. So the entropy was introduced by Clausius in 1860s. Now, entropy, as I have mentioned earlier, that is related to the amount of disorder or the state of the system. So, if we are going to express it in equation we have here, delta S, or S we use for entropy, or a change in entropy is equivalent to Q over the temperature T, wherein the temperature is in Kelvin. So that is the quantitative description of entropy, wherein delta S, or change in entropy, equals Q over T. And also take note that change in S is always greater than 0, or is always positive. So that means the entropy, or the amount of disorder, always increases. Okay? So this now explains those processes which are irreversible. That there are only idealized processes which can have a delta S of equal to 0, or no change in entropy. However, real natural processes, we have delta S is always greater than 0. And we can also have another expression of second law of thermodynamics. Okay, based on that, so we can also express second law as this one. We have here the total entropy of any system plus that of its environment increases as a result of any natural process. For example, we are going to think about the universe. If the entropy increases at some point, there are also some point wherein the entropy decreases. But if we are going to sum up the entropy of those systems, the change in entropy is always positive, or always greater than 0. So still, entropy increases. The natural processes tend to move toward a state of greater disorder. So that is all about the second law of thermodynamics. So you can use this in case pinagalitan kayo na laging makalat ang table nyo, or laging makalat ang area nyo. It's because of entropy. It's the second law of thermodynamics. There is always a tendency to move towards a greater disorder. Okay? So that is the second law of thermodynamics. Okay, before we end this one, I'll show you some applications of heat engine and second law of thermodynamics. We have here pumping heat against its natural flow. Air conditioner transfer heat from cold object, your home. So for example, your home is already cold because of air conditioning system. Still, you are transferring heat from cold object to a hot object, which is the outside air. But the air conditioner always has to use ordered energy in the form of electricity when it pumps heat from a colder object to a hotter object, because it's not the natural flow of the heat. The greater the temperature difference between the indoor air and the outdoor air, the more electrical energy the air conditioner must consume. That's why it's very practical that if it's very hot outside, kahit gustong-gusto nating mas malamig yung air conditioner or air conditioning system natin, it would be ideal to somehow increase the temperature of the air conditioning system if you wanted to conserve or save electrical energy. Okay? So the less the difference in the temperature, the less electrical energy consumption there will be. Okay, another example or application of this heat engines would be the heat pumps. Okay, we are not using here this one in the Philippines, but of course, for those who have, or for those which have cold temperatures, they have these heat pumps. It's a geothermal system, uses water chilled under the ground to keep cool your home. And then, but during winter, a geothermal system also uses water which is warm underground to help heat your home. Okay, so those are heat pumps, but again, it has to consume electrical energy. So another example is the deep sea air conditioning system. So you have here, seawater is being used to cool the buildings. This is in Mackay Ocean Engineering in Hawaii. Instead of using compressors to cool the water in their operating system, the systems designed by Mackay used frigid water from the ocean's depth. However, they have to ensure that the layer for the exhaust, that the temperature of the exhaust or where the exhaust will be, it should be almost the same temperature do sa seawater. Yung exhaust temperature ng exhaust should be at the same layer do sa seawater level with that or same temperature so that there will be no imbalance in the ecosystem in the ocean. But this one, about 10% of the electricity of current methods, and it saves fossil fuels and a lot of money. But again, they have to ensure the safety of the ecosystem found in the ocean. Okay? So that is another application. Now, there was also a third law, that is the Neurons Theorem, developed by Walter Nernst during 1906 to 1912. As the system approaches absolute zero of temperature, all processes cease and the entropy of the system approaches to a minimum value. So as the system approaches the absolute zero, the entropy or the amount of this order will also be at the minimum value. But I have mentioned that it will be very impossible to reach the absolute zero temperature. So really, let's accept it that in the natural processes, there would be amount of disorder and it's increasing. Okay, so that would be the end of the conceptual part of this discussion. I will upload another video wherein we will be solving sample problems on second law of thermodynamics. Okay, so I hope you learned a lot from this session. Goodbye, everyone.